All right. So um let's have to draw it. Let's draw it. We have to draw it. So say we have here, this is the curve, okay, and then this is the tangent line of the curve, okay. So at point xy, okay, and then it is said here that the x-intercept, when you say x-intercept, by the way, if you have a certain line, straight line, y-intercept is the point in the y-axis where the line intersects. So this is the y-intercept. And x-intercept is the point where the straight line touches the x-axis. So this is what you call x-intercept. So if this is the tangent line at a certain point xy of a function, of a certain graph of a function, then this is the x-intercept, and the coordinates of this x-intercept, let's say x-intercept is represented by xi, okay, then 0. So these are the coordinates. Of course, x-intercept has a 0 ordinate, okay, and it is said here that the x-intercept, okay, of the tangent line at any point xy divided by the square of the ordinate. So since the point where the tangent line exists has the ordinate y, so the square of that is y squared, then x-intercept divided by ordinate squared is said to be constant. So let's say that constant value is represented by k. Alright? So we have 2 points in this figure. This point and this point. Now remember, for a slope of a line, if we have 2 points P1, which has the coordinates x1, y1, and P2, which has the coordinates x2, y2, the slope of the 2 points of the line is you have y2 minus y1 over x2 minus x1. So let us say this will be our first point, and this will be our first point, and then this will be our second point, so that the slope of the tangent line is equal to have y minus 0 and x minus xi. Alright? Or this is y over x minus xi. Okay? And this is equal to, remember, slope of the tangent line is dy over dx. So from here, we already have a dE. Okay, so we just have to solve this dE to get the equation of this curve being defined in the problem. Okay, but our dilemma here is that we have xi. Now we have the derivative dy over dx, so that all the variables involved should only have y and x. And since we have here xi, we have to eliminate or convert this into in terms of y or x or whatsoever. And we will be assisted by this equation, okay, that is stated also in the problem. So we could express xi in terms of y squared. So xi is k y squared. Okay, so that we have to substitute it here. So we now have a new equation, dy over dx equals, we have y over x minus xi, okay, which is k y squared. Now what I can see here is that if we try to have dx over dy, that would be equal to x minus ky squared all over y. Okay, so that this becomes x over y minus k times y equals dx over dy. And then we try to transfer x over y the other side, so we have dx over dy minus x over y equals negative ky. Now this is a first order linear DE. Alright, so since x here is deemed to be the dependent variable and y the independent variable, so our p and q should be functions of y. So here, function of y times x is negative 1 over y, and our q here is negative ky. Alright, so I guess we have to use another paper. Okay, so to continue, we have integrating factor equals e raised to integral of p dy. So we have e, then we have negative dy over y, so that is equal to e negative ln of x, or that is x raised to negative 1. So for the solution, we have or rather y pala, y. So y raised to negative 1. So you have x times integrating factor y equals negative 1. So we are just applying here the first order linear DE. Okay, method. And that is equal to integral of the phi y negative 1 and then q negative ky dy plus c. Okay, so we have x, y negative raised to negative 1. And then we have y negative 1 times y becomes y raised to 0 or 1. So we are only left with negative k dy integral plus c. So we have x, y negative 1 equals negative ky plus c. Okay, and therefore, to simplify, we have to multiply everything by y, so that we'll have x equals negative ky squared plus cy, or we could have x plus ky squared, okay, equals cy. So this is now the equation, okay, of the curve being described in number 2. Now, as you can see, there are two constants, k and c. So we can't get the particular solution because we are not given boundary conditions in this problem. So we could only get the general equation of the curve being described in number 2. Alright. Okay, next question, next example for geometric application. The part of the normal to a curve at any point xy on the curve. So let's say this is the curve being described, and this is one of the points with the ordinates xy. Okay, now the normal curve, so if this is the tangent line at this point in the curve, therefore this is the normal line at this point in the curve, which is always perpendicular to the tangent line. Okay, so this is the normal line. Alright, now the point or the part of the normal curve or a normal line, okay, between this point xy and the point where the normal meets the y-axis, or this means the y-intercept. So this point, the y-intercept, or where the normal line meets the y-axis, okay, is bisected by the x-axis. This only means that this part of the line from this point to this point, okay, this whole line here is being bisected by the x-axis. When you say bisected, meaning you are dividing a certain line into two equal parts. Therefore, if this line from here to here is being bisected by the x-axis. Therefore, this point of intersection of bisecting of x-axis from here to here and from this point to this point, it's equal. So this distance, okay, this distance, okay, and this distance is equal, okay, because this is the point of bisecting, okay. Right. So if this is equal, this distance and this distance, therefore the height from the origin, okay, the height here, which is y, because the ordinate is y, so meaning the height is y from the origin. Therefore, the height also here is y, okay, since the lengths are equal. And that will also mean that this point, okay, has the coordinates negative y, 0, negative y. Okay, negative kasi it's below now the origin as being described in the drawing. Okay, so we now have 2 points of the normal curve. We have xy and 0, negative y. So let us say this is our first point and this is our second point. Now, the slope of a normal line at a certain point is just equal to, as I've said, negative dx over dy. So from what we have reviewed earlier, okay, the moment of the normal line is negative dx over dy. At the moment, the slope pala. Okay, right, so we have here equals, okay, the slope of this normal line, so we have the ordinates, difference of the ordinates, you have negative y minus y all over, okay, so you have ordinate, second ordinate minus first ordinate all over second abscissa minus first abscissa, which is x. Okay, so this becomes negative dx over dy equals negative 2y over negative x. So since they are both negative, this is still 2y over x. Okay, so negative over negative is positive. Okay, so I guess we could do variable separable. So we'll have negative x dx equals 2y dy. Okay, then let's have it 2y dy plus x dx is equal to 0. So integrate both sides. So we have, this is y squared, 2y dy integral is y squared plus x squared over 2 is equal to c. Okay, and we could multiply everything by 2 so that we could have 2y squared plus x squared is equal to 2c, or still that is a constant c. This is now the equation being described in number 3. Okay, so that's it for the geometric application for first ordered differential equations.